Module 6, Single Lane Design, Design Details. Angle between approach legs. Generally preferable for the approaches to intersect at perpendicular or near perpendicular. This results in relatively slow and consistent speeds for all movement. And you're going to want to consider realigning the approach when the intersection angle is less than 75 degrees. If you have significantly greater than 90 degrees, this often results in excessive speeds for one or more right turn movements, as shown in the graphic on the right. Significantly less than 90 degrees makes it really hard to accommodate the right turning design vehicle. Angles of visibility. The intersection angle between consecutive entries must not be overly acute in order to allow drivers to comfortably turn their heads to the left to view oncoming traffic from the immediate upstream entry. Based on guidance for designing for older drivers and pedestrians, the recommended minimum angle for visibility to the left at entry is 75 degrees. The exhibit on the left shows a driver at the yield line really having to look over their shoulder to see oncoming traffic. So this is a very challenging entry design there. And the one on the right definitely shows an improved angle, easier for these vehicles as they're approaching and sitting at the yield line to be able to see oncoming traffic from that adjacent entry. Splitter islands. They provide refuge for pedestrians. They assist in controlling speeds. They're going to guide traffic into the roundabout and separate entering and exiting traffic streams. They're also there to deter wrong way movements and provide a location for signs. Splitter islands generally extend upstream of the entry line to the point at which entering drivers are expected to begin decelerating comfortably. The higher the approach speed, typically the longer the splitter island, can extend beyond the end of the exit curve to prevent exiting traffic from accidentally crossing into the path of approaching traffic. FDOT requirements on minimum length based on the design speed of the approach leg are: for 35 miles an hour or less, we're going to look at a minimum of 50 feet, 45 miles per hour or less, minimum of 100 feet, and for higher speed approaches, as we discussed previously, which is 50 miles per hour or greater, we're going to look at a minimum of 200 feet. The minimum width within the pedestrian refuge area is 6 feet, and 8 feet desirable at this location, providing enough space for somebody pushing a stroller or a bicyclist to sit in this refuge area. The minimum crosswalk width within the splitter island is 10 feet. And the location of the pedestrian crossing should be 1 car length or approximately 20 feet upstream from the yield line. The FDOT splitter islands are to use either a type E curb and gutter, which will have that 1.5 foot gutter, or a traffic separator or type B curb with a 1 foot offset. And the exhibit shown below is from the FDM and calls out all the different dimensionings that you should be following. Entry design. The entry radius is an important factor in determining the operation of a roundabout because it affects both capacity and safety. It also controls the amount of deflection imposed on the vehicle's entry path. The minimum entry radii should be approximately 65 feet, and you'll find on single lane entries between 60 and 90 feet is typical, although there may be locations with larger design vehicles that you may use a larger one. The capacity will increase with increased entry radii, but so may the entry speed. And we just want to be clear that the entry radius is not R1. This graphic shows that typically that outside radius is greater than 65 feet. But again, if you are looking to accommodate a WB62FL, you may require a larger outside radius. So we want to provide adequate curvature on the entries to channelize drivers into the circulatory roadway to the right of the center island. We also want to provide enough curvature to block a direct path to the center island. And this helps avoid vehicles errantly hitting the center island but it also further discourages drivers from making a wrong way left turn. Exit design. Exit curb radii are usually larger than the entry curb radii in order to minimize the likelihood of congestion and crashes at exits. This is balanced by the need to maintain slow speeds through the pedestrian crossing on exit, and your exit design is going to be influenced by the design environment, pedestrian demand, the design vehicle, and other physical constraints. The exit speeds may be controlled by the exit path radius, that R3 that we had measured previously, but is more often controlled by the circulating path radius, that R2 plus acceleration. We want to ensure that entries are slow and circles are compact enough to keep exit speeds low. Flatter exits may cause drivers to accelerate out of the roundabout, but the sight of the exit crosswalk is improved. So here's a graphic of a curvilinear exit type of design. So there's a little more curvature on this particular one. And here's a picture of a design that has some curvature on the exit. You can also have a large radius exit design. You can see this is pretty straight out, and this is again typical with our offset left approach alignment design that we're recommending. And you can see this one has a much straighter out type of exit with that large radius exit design. So let's take a look at the DOT policy for exit radius, and they recommend 300 to 400 feet should be provided to create a smoother vehicle path and better truck accommodation. This should balance the competing objectives of accommodating the design vehicle and providing a safe environment for pedestrians. And we want to provide flat exit geometry when no pedestrian facilities are present. Entry and exit widths. Narrow entries and exits tend to promote lower speeds, improve safety, and provide shorter pedestrian crossings. A WB62FL may require 17 to 21 foot wide entries and exits for single lane roundabouts to be able to make a right turn. We want to accommodate a right turning WB62FL without encroaching into the truck apron or curb and gutters. So if we take a look at the picture here, you'll notice an entry. It's got quite a bit of curvature, so the speeds look like they are a little bit slower. But what you'll notice is that it does not accommodate the design vehicle appropriately because there is some over tracking behind the curb and gutter. So this now becomes a maintenance issue where the entrance should have been made a little bit larger to accommodate that design vehicle. Entry and exit width example. This is a nice example showing the flaring of the roadway as we approach the roundabout. Starting off with a 12-foot lane here that widens out to 16, and near the yield line widens out even more to 19, again to accommodate that right turning design vehicle. Have a little extra width in the circulatory roadway, and then 20 feet out on the exit. Now this one was designed for a WB67, so a little bit larger design vehicle, knowing that the WB62FL is the standard. But this is a good example of just showing the widening as you're approaching the roundabout, and then the tapering back down as you exit out of the roundabout. Curbing. Curbing gives drivers a sense they are entering a more controlled setting, causing them to naturally slow down. It helps improve delineation and to prevent corner cutting, which helps ensure low speeds. And low speed approaches typically incorporate 6-inch vertical face curbs on both sides of the roadway. Roadway width. The width of the roadway at locations with curb and gutter on both sides should accommodate the design vehicle. And the face-to-face widths for entries, exits, and bypass lanes is 15 feet. So that again is typically your 12-foot lane with 1.5-foot gutters on both sides. Circulatory roadway width. This will be determined from the number of entry lanes and the turning requirements of the design vehicle. Want to only provide the minimum width necessary to serve the required lane configuration. Typical lane widths from 16 to 20 feet for single lane roundabouts. And too wide at single lane roundabouts may cause drivers to think that two vehicles can circulate side by side. A truck apron is often needed to provide additional circulatory roadway width to accommodate larger design vehicles. And typically you're going to want to accommodate buses without having to use the truck apron. Circulatory roadway slope. We're going to want to slope the circulatory roadway away from the center island at 2% with a 1% minimum. Central island. So this is the raised, mainly non-traversable area surrounded by the circulatory roadway and typically includes that traversable truck apron. Also includes typically landscaping for aesthetic reasons and to enhance driver recognition of the center island. And the inability to see through the roundabout reduces or eliminates headlight glare at night and driver distraction by other vehicles on the circulatory roadway. Truck apron provides additional paved area to allow the overtracking of large semi-trailer vehicles on the center island without compromising the deflection of smaller vehicles. And in Florida, using the specific color red as shown there, and the graphic shows what that red looks like for the concrete truck apron. Here's an example of a well-designed roundabout that is accommodating that design vehicle, and you see the rear wheels of the truck overtracking onto the truck apron. Sometimes the truck apron may need to be widened to accommodate oversized, overweight vehicles, and this is a location that you can see that the truck apron is widened in this particular area to accommodate for that larger design vehicle. Right turn lanes. At locations with a high volume of right turning traffic, a right turn bypass lane may allow a single lane roundabout to continue to function acceptably. A right turn bypass lane should only be implemented where needed, and entries and exits of bypass lanes increase conflicts with pedestrians and bicyclists. Here's an example of a free flow right turn bypass lane. So they totally bypass the roundabout altogether and there's no yielding. There's an acceleration distance that you'll need to have them running parallel, followed by a taper back into that single lane. This picture shows free flow right turn bypass lanes. You can see the one here on the bottom, right turn, bypasses the roundabout altogether and actually heads into its own lane. And the same with the one on the top, again, is another free flow bypass lane that eventually does merge into a single lane and onto the freeway. Another example of a right turn bypass lane is a yielding type of bypass. So it's a partial right turn bypass. So they would come up to a yield line, wait to anybody exiting out of the roundabout, and then make their right turn. And what we want to do is we want to snag that or make it obvious that the driver that's making that right turn that they should not be going into the circulatory roadway. So you want to design it in a way that they're pointed at that splitter island and not into the circulatory roadway. Here is another graphic, or another picture I should say, showing in this case right turn bypass lane. So you can see a partial right turn at this location as well as a partial right turn there. So those are single lane partial right turn bypass lanes. And actually on the top here, you can see that this is a dual partial right turn bypass lane. This picture shows a free flow right turn bypass lane as well as partial right turn bypass lanes on this leg as well as the other two legs. And the third one is where you'd actually have just a right turn lane. So you have a two-lane entry and the rightmost lane becomes a right only. And many times when we do that, you may want to introduce this painted gore as shown on the right example. And again, we want to make sure that that splitter island blocks the through path to emphasize that that is a right only. Now you've introduced a two-lane entry, which can be a little more challenging to control your entry speeds as well. And here's an example of an entry design that has a right turn lane in it. You can see that it flares from a single lane to two lanes, the left one being a left through only and then the right turn only. Right turn lanes and the crosswalk pros and cons of the different alternatives. The one on the left is the free flow, so potentially a little bit higher speed with that, crossing two different crossings at that location. Yet the driver, as they're approaching, doesn't have to worry about vehicles circulating, so they can focus in on the pedestrian without having to look to the left for vehicles and exiting out of the roundabout. The one in the middle is our partial right turn bypass. So again, as the vehicle is sitting at the yield line there, they are looking to the left, and then just to the right is a crosswalk. So they're going to have to keep, be aware of the pedestrian that may be crossing there. They are taking this two-lane entry and splitting it up with this splitter island, so the pedestrians do have shorter crossing distances and can do it one at a time. And the one on the right here does have this two lanes that they need to cross. And again, just downstream after they've made that right turn is the crosswalk. So there's not necessarily a right or wrong. Each has its advantages and disadvantages, and just things that the designer needs to keep in mind when they choose which one to use. Here is another graphic of in this case, a partial right turn bypass lane. And actually there are two lanes that are approaching this roundabout, and the rightmost lane is becoming a right only, so really kind of dropping a lane. But I'll just ask, is this right turn well designed, or is it is it snagged, or is it actually easier to get into the circle in that lane as opposed to the one that they're supposed to be in, which is in the left in the through. So this one you'd want to look to put a little more curvature potentially on that right turn and try and snag it a little bit better and get it directed at that splitter island. Here's another example of a right turn bypass lane that really was added for no operational reasons. So we would recommend that these actually don't get constructed, because all you're doing is adding additional conflict points and potential confusion for the driver. But this design, due to the angle, has kind of a sort of a race to that spot, with vehicles circulating and exiting out of the roundabout, and then vehicles in this right turn lane. So that angle isn't necessarily the best. Here's where the yield sign is placed, and we have our driver sitting there, so they need to then look over their shoulder. So that's a pretty harsh angle to be looking back for somebody circulating. In addition, there's plantings in this area as well as a light pole. So the sight line is over the shoulder and will be blocked by this landscaping. So they're going to actually want to cut that down so that vehicles in that right turn bypass lane can see the vehicle circulating. And one final thing on right turn bypass lanes, in order to accommodate this larger right turn vehicle, in this case the WB62, these drivers we can make our design so that it is acceptable to use both exit lanes to accommodate the design vehicle. If you weren't to do this, you're going to get if you're trying to make them turn into the rightmost exit lane, your right turn is going to get really fast, and so it is acceptable to allow them to use both exit lanes here, which can help keep that right turn speed down. And really, a truck sitting there is not going to pull out next to a car or another vehicle that is circulating. So that concludes Module 6, at least the lecturing part of it. What we're going to move into now is a single lane design, and I'm going to go ahead and design the west leg of a single lane roundabout. Let's talk about our example that we have here. Pretty squared 90-degree intersection. We've got different approach speeds, which are going to have different requirements for length of splitter island. Looks like we've got plenty of right-of-way at this location. We're not going to want to have any impacts in that southeast corner because we've got some parkland there. On the north side, there's an existing bridge that needs to remain. So we've got some different constraints and some different issues that we need to take into account when we are designing this. But it is a higher speed. The east-west is 55 miles per hour posted, so our design speed is 60. So we're going to want to use the high-speed approach type of design for those particular legs. And again, I'm going to be looking at the west leg here. So we'll be looking at that 60 mile per hour design speed. More of a rural setting and some generous right-of-way there. So we're going to, let's determine what our ICD that we should be using. Again, we should be in this 120 120 to 160 foot range. So again, we've got this real high speed, we've got adequate right of way, we've got a large design vehicle. We're going to be accommodating that 62 FL. So, at this particular location, I would always start large. It's a little bit easier to accommodate the design vehicle and to control your speeds when you have a larger circle. So in general, try to use a little bit larger circle if and when we can. And then our circulatory roadway width that we'll use, normally between 16 to 20 feet for single lane roundabouts. Again, a little bit larger circle, so we're going to go ahead and use, in this particular example, 20 feet for our edge of pavement to edge of pavement circulatory roadway width. For our design example here, we're going to be following the FDOT Exhibit 213-2. And if you recall, we've got this curve to the right, tangent, curve to the left, tangent, and then curve back into the right. And all of the approach speeds and information that we're going to be using are shown in this table. So we've got 60 miles per hour, so we're going to be using this 1800 and the 950 for our curves that for our R1 and our R2. So with that, I'm going to go ahead and hop into MicroStation and start the design of the west leg for this single lane roundabout. We have our CAD file opened up here in MicroStation, and we'll go ahead and design or do a conceptual design for the west leg of this particular roundabout. What I'm about to show is just an alternative, something that works for me. Everybody's going to design it in a different way to meet the requirements where we want to control our entry speeds and accommodate the design vehicle and make a roundabout design that has good composition and is well balanced. So again, this is just one way of doing it. It's not necessarily the way that I do it all the time, but it's just a way to show you how to design the west leg based on the FDM design exhibit that's out there. So the first thing I'm going to do is I'm going to go ahead and I'm just going to trace over the center line here of the roundabout, or of the roadways, I should say. So now that I've got that established and I know based on the right-of-way impacts or the right-of-way that's available that I'm just going to place this roundabout in the center. So I'm going to turn off the topo there. I've got that established. I've got a little area over here where I've got some different levels available. So I'm going to just select that. We had decided we're going to use a 160-foot diameter circle. So I'm going to go ahead and place that right in the center of the circle. I'm going to go ahead and offset that 20 feet. That will be our circulatory roadway in between those two lines there. I'm going to go ahead and draw in the curb. So I'm going to offset a 1.5 foot gutter to the inside for our central island, 1.5 foot to the outside, 1/2 foot to the outside for that gutter or curb head, and then actually, 0.75 for the inside for that curb and gutter there. So we've got our circle placed, we've got our circulatory roadway all set to go. If we were to turn on the topo, we can see that it fits nicely in there. Again, nice 90-degree intersection, so no reason to necessarily push it one way or another. We may need to make some modifications on the south leg to have no impacts to the park, but to start, we're going to just go ahead and center it within the existing roadways. So to get started for the west leg, one approach here would be to go ahead and we know we need a 200-foot splitter island due to the higher speed approach. So I'm going to offset this edge of pavement 200 feet. And that's where we want our splitter island to be at least that long. We know that we want to have a 10.5 foot nose. We need 10.5 feet at that point. So I'm going to do half of that, which is 5.25. And that's going to be our nose there, the place that we want our splitter island to begin or end. I can go ahead and delete that. So this is 200 feet away from the circle. And I'm going to, for this particular example, have all of our island growth to the right of the center line. So as a driver is approaching the roundabout, they're going to have to shift over that 10.5 feet. Options are, again, depending on where that circle is located, whether it's split or pushed to the left. But for this example, we're going to have everything to the right. So let's go in and draw some arcs. Here I'm going to put some things on some different colors so it's a little bit easier to see. I'll do a light blue. Our first arc at the beginning is a 1,800. And I'm going to make that tangent to our roadway, our center line, and just kind of eyeball something in here and place an arc like that. Our next arc is going to be 950, and that's going to be the curve to the left. First thing I'm going to do is well, actually I'm going to go back in and do that 950 here and make that tangent to here. And I know I need to get a tangent in between there, so I'm going to, make sure that there's some distance in there. So there's that arc placed. Again, I'm just kind of eyeballing it here. Again, everybody's going to do it a little bit differently. I'll go ahead and put that tangent in there, and I'm going to put that on a different color. And we'll do red. So I'm going to draw now a tangent between those two. And I'm going to trim those up. And this arc, or this tangent, I should say, we want to be at least 100 feet. So this is 132 feet. So we've got our curve to the right, we've got our tangent, and then we've got a curve to the left. The next thing we'll look to do is draw a radius into the circle. And the first one I'm going to do here is I'll just do a 90 foot into the circle. I'm going to make a tangent to the central island there. Again, knowing that I'm going to need some tangent in between there. Do that. Go ahead and draw a line in between there. Trim those up. And I'm at about 78 feet. So greater than 100 for this one, greater than 50 for that one. I've got a curve to the right, a tangent, curve to the left, tangent, and then that arc into the circle. I'm going to go ahead and offset these lines. Got a 12-foot lane, so I'm going to offset this 12, this 12. I can just do this one. Whoops. This one and this one as well. Okay, so there's our entry. I'm going to go ahead and put in the controlling radius into the circle. I'm going to make, that one, let's say 85 feet from there to there. Okay, so we've got, a real conceptual design laid out. Next thing through the process would be what we learned previously is go ahead and check the fastest path and then see if it accommodates the design vehicle. So let's do that fastest path check again real quick here. Just getting my, again, levels all set up here. If you recall, we offset this 165. Whoops. Make sure we're using there we go. And then we're going to offset another 25 twice. We're going to do 5 feet from the face. Well, this is the edge of pavement. So this will actually be 3.5 feet. So we'll offset this 3.5 feet, 3.5, 3.5 here. And I don't have an exit, and that's okay. All I'm doing is really doing a quick, fastest path check just to see if I'm in the ballpark there. I'm going to put that on the fastest path level. And if you recall, we're going to do a spline here, which is there in the different settings that we've got. I'm going to go ahead and select our 3 beginning points. We're going to do the one there, one here, one about where I think a crosswalk is going to be, and then 3 just out on the exit. Again, just a real quick fastest path check here to see. And as we refine the design and get a little bit closer, we can make modifications to this. You can see this one's going to have to come down a little bit. Some modifications here. Oops. Okay, so we're kind of good at the beginning here. There, close in the circle. So, again, we're doing a real quick check here, so no need to get it perfect. We'll check and see what this radius looks like. And again, I like to draw a circle in here, make that about 70, and then draw an arc over the top. And we see that this arc, if we measure it here, is 127. If we had our spreadsheet open, you could go in and figure out the speed on that particular one, and we'll know that it's underneath 25 miles per hour. So we know that that is a good entry or speed control design there. So we're controlling our entry speeds. The next thing to do would be then to check our truck accommodations. So what I'm going to do is I'm going to actually go ahead and draw a quick exit here. I'm going to turn off those fastest path checks there. And we'll draw in an exit, and I'm just going to make this pretty straightforward and easy. We're going to take and extend this arc around. I'm going to go ahead and do a 400-foot exit radius here. Go tangent off of that alignment and draw that in. So there is what potentially could be an exit there. I'll go ahead and change that color just to give you a better idea there. We'll make that green. All right, so now let's go ahead and check our truck, and this is going to be an eastbound left. So I'll go ahead and get that on the right level here. As they're approaching the roundabout, a lot of times I'll center them if the radiuses are large enough. So there's 6 feet there. We'll do 5 feet off here, and we'll just do 5 feet out the exit as well. Go ahead and put a tangent in between these two. Connect them. Make that complex chain. So we've got it following around, and then we can just kind of run the truck through here as well, which is the WB62 FL, and then we can go through and look and check our design. You can see that the truck is going through nicely, but it is overlapping a little bit and getting into the gutter here. So maybe we need to go ahead and either put in a larger radius, or we may need to come off of the circle a little bit here. So let's say we do maintain that 85-foot arc, but we just come a couple feet off of the circle, let's say, and we put it like that right there. You can see that, well, maybe just a little bit. So maybe we need to go back and do, let's just try a 90-foot arc with that same offset. So you can see that the truck is now accommodated and goes through, and it's not getting into the gutter. What we did do here, though, is we did change our fastest path. So this is where the iterations come in. So I'm going to go ahead and turn that truck off. And this is where we would go back now and check our fastest path. We'll offset this again, 3.5. So that's our new offset line. We'll delete that. That's our radius, but I'll go ahead and do this path through first, modifying this PI to there, the beginning. Make that look good, and then around the circle here. Okay, so again, we've updated our fastest path, and things look pretty good there. We'll go ahead and check the radius. Delete this one. Whoops. It looks like my circle might be a little bit better if it was over here. And we'll see now that our radius here is 134, so we'll just want to go in and check and make sure that that is under 25 miles per hour. Oops. And this is 134. So there's a quick example walkthrough of the iterative process of designing a single lane entry based on the Florida Department of Transportation's FDM, that exhibit that's shown in there for high-speed approach. We have a splitter island that's 200 feet back. We're using the appropriate radiuses depending on the approach speed. We've provided the tangents that they're looking for the minimums, if not a little bit more. We are providing an appropriate fastest path, and we're accommodating the design vehicle.